welcome to the second part of this series of lectures on catalysis. And it gives me great pleasure to introduce an old friend, collaborator, Professor John Anderson, who came all the way from down under to give these lectures. He's university, and he joined the faculty there after, was it 15 years as the chief of the 16, as the chief of the Division of Material Science of the Commonwealth Scientific and Industrial Research Organization in Melbourne, and as chief of that. Thank you. Yeah. As chief of that institute, he presided over work in material science, surface science, and catalysis. And we have collaborated over a long period of years on various matters, and for the past 10 years on a series of books on catalysis science and technology, 9 of them now in press. But John Anderson has been a prolific writer in the field of catalysis, and I think that he's going to start by showing you a list of books that I see here, but there they are. And at least the first one and the third one is on. What we have done so far is sort of give main ideas on the catalytic functioning, on the functioning of catalytic cycles, with great emphasis on the power of thermodynamics in helping us to understand how they turn over. From now on, I think you will get a much more concrete approach with description of the chemistry and the physics of catalytic materials, especially. So, John, it's all yours for a few weeks now. Handouts for those who want to pick them up.
Good. Well, welcome to the course. As Professor Boudard pointed out, I've got on this sheet, which I hope you can read satisfactorily, some reference books, which I'll on occasions refer to during the course of the next 15 lectures or so. They're not, in a sense, required textbooks. There's no suggestion that you have to buy them. They're, in fact, available on reserve in the university library. And from time to time, I'll make a suggestion when it might be worth your while having a look in a bit more detail about some of the topics we speak of. The first of these books, which, as Michelle pointed out, I wrote, is really an essay on the structure of, as the title tells you, the structure of metallic catalysts. It tells you something about their physical and chemical nature. The second book in the list is a recent publication by Bruce Gates. Let me briefly summarize what we said in the lecture on Friday. We were talking about ways of preparing dispersed metal catalysts. I pointed out that if you were using a porous support, which was typical, such as gamma alumina or silica gel or some such, the metallic precursor could be introduced into the porous support in one of two distinct ways. That is by occlusion of solution, where the solution is drawn into the pores of the support by capillarity action, and then the solvent is driven off. The solid precursor is then decomposed and reduced to a particle of metal. Or alternatively, the molecules of the metallic precursor can be adsorbed on the surface of the pores, and the adsorbed species, after removal of the solvent, the adsorbed species can then be decomposed and reduced. And in the process of being treated in that fashion, the individual metal atoms migrate across the surface and form small crystals, which are the aim of the preparative procedure. This next display, which is on page 5, merely summarizes some of the solute absorption processes, or gives examples, and I don't propose to do anything other than just indicate very quickly what's at issue here. S means surface, so SOH means an OH group bonded to a surface of some sort of the support. And the first example is simply a case where the hydrogen atom, the proton of the OH, is acidic. It can dissociate to H+ and be replaced by an incoming cation. And the adsorbed species is as indicated here. In practice, I might point out that it's not uncommon to first replace the H by, say, a sodium ion, and then exchange the sodium ion with the platinum tetramine. But that's a minor matter, but you can understand the principle nevertheless. Typical substances in which some of the OH groups at least are acidic are zeolites, silica alumina, and even silica itself has surface OH groups that have some degree of acidity and which can undergo an exchange process of that sort. Alternatively, the OH groups on the surface may have a basic character, that is to say they can actually pick up a proton to form some sort of protonated species. As I've suggested there are some groups on the surface of gamma alumina that are basic, but a better example perhaps would be the OH groups that are present on the surface of magnesium oxide, which are strongly basic and which can undergo a reaction of that sort. Binding a proton generates a site with a positive charge, which can then bind a negatively charged cation. And the third illustration here is the ligand exchange process, or an example of a ligand exchange process, which I mentioned last week, namely where for instance, the oxygen in the surface, which might start life as a surface OH, functions as an actual ligand and is bonded coordinatively to the metal atom. And the last two lines just remind you that ligand exchange processes are also possible with clusters. The first example is triosmium dodecacarbonyl, which has been in fact extensively studied by Gates and a number of others, which interacts with surface OHs on substances like gamma alumina after the fashion indicated here. Removal of CO and bonding of the osmium to some of the oxygen, and in fact in this case it's alleged the proton, which was originally part of the OH, becomes a hydrido ligand on the osmium. And the second example is a nickel allyl complex, which loses one of the ligand moieties, and its place is taken by the oxygen on the surface of the solid. There are many possible variants to that sort of procedure, but these are just examples which give you some idea of what is the principle, what the style of reactions that may take place. At the bottom is a statement which you need to recall, you need to remember. That is, in general, solute adsorption gives you better dispersion of the metal than an occlusion process. The problem is, of course, with occlusion you have little control over the size of the metal particle because it depends very largely on the concentration of the solution being used for the impregnation process, and also upon the actual size of the volume of the liquid which is included in the pores of the support. And the result may well be that, and very often is, that with occlusion you get largish metallic particles. If you want well-dispersed metal, you're better off, if you can, to work with solute adsorption or precursor adsorption techniques. And finally, before leaving this question of how you go about these preparations, let me just remind you about what might happen if you have a mixture of solutes, which may be required if you're making an alloy, if you wish to have a dispersed alloy. If you're proceeding by an occluded precursor technique, then there's little problem because the occluding solution might very well contain both solutes. For instance, precursors involving, say, platinum and gold. The occluding solution may contain both solutes which are precursors to both of these species at the start, and the result will be that when the particle is formed, it will necessarily have both platinum and gold atoms. To take that as an example, it will have platinum and gold atoms in it. However, problems may arise when you are dealing with adsorbed species, and I don't want to spend too much time on this, but let me just very briefly point out the sorts of problems that occur. You recall that irrespective of whether the solution is entering the porous support with the intention of working with an occluded solute, or whether you're working with adsorbed solute, the liquid has to penetrate through the porous mass of the support. If you have two components, both of which are adsorbed on the surface of the support, and if they're adsorbed with different strengths on the surface, that is, if component A is adsorbed more strongly than component B, then as the liquid penetrates the pores, the more strongly adsorbed component will be adsorbed on the surface preferentially. And so during the process of introducing the solution into the pores of the support, you get a sort of chromatographic separation of the two metallic precursors. The more strongly adsorbed one tends to be adsorbed towards the outside of the support pellet, and the more weakly adsorbed one is carried through into the interior. And that can be a nuisance because it means that when you come to do the decomposition and reduction process to generate the metallic particles, you're starting off with the metallic precursors which are physically separated in the pores rather than being all mixed up together. There's not much you can do about it. It's a problem that you have to live with usually, and rely upon surface diffusion during the thermal and reductive treatment to homogenize the metallic species and produce a collection of alloy particles. Well, now, what are we to say about the structure of dispersed metal catalysts, small particles? Let me begin by saying that in general, what you have is a surface structure which is rich in surface atoms which are of low coordination, that is to say, which only have a relatively small number of nearest neighbour metal atoms. This is true even though one is dealing with particles of ideal crystallographic shape. I'm now speaking about item 1 here. In practice, of course, one very seldom gets, in practical catalysts, one very seldom gets metallic particles of ideal crystallographic shape. The particle shape is usually dictated by the history of the preparative procedure. But in certain special cases, not of the style we've been talking about, but often in vapor-deposited metal, particularly when it's deposited on a single crystal such as cleaved mica, or say the hexagonal surface of sapphire, you can get particles, small metallic crystals of ideal shape. It might be octahedrally shaped particles or whatever. But even those are usually only found and can only be characterized when they're in excess of 100 or 200 angstroms in size. And most of the particles which one is dealing with in supported metal catalysts are a good deal smaller than that. But it's worth having a look at a few of the ideal crystallographic shapes, which, if they did exist, would be what you might observe, assuming that one had the techniques to actually observe them at the size they exist. I've taken these 6 simply out of the atlas of these things, which is presented in the book Structure of Metallic Catalysts. And if you want to have a look at the others, you can have a look at the book in the library. I just want to point out to you a couple of things. To take this octahedral shaped particle over here, this is for a face-centered cubic system. Note that and this is where each of the faces on the octahedron is a 111. There's a 111 metal surface. In a 111 metal surface, the atom in the surface plane has 9 nearest neighbors. 9 nearest neighbors. There's 6 in the plane itself and 3 below. That means, in fact, that it's lost 3 nearest neighbors in becoming a surface, because an atom buried in the center of a face-centered cubic metal has 12 nearest neighbors. But anyway, there are 9 nearest neighbors, whereas at a corner position out here, the atom only has 4 nearest neighbors. And this has, of course, been known for many years, and it's been speculated endlessly that the difference in the coordination of atoms in low index planes such as 111 or at corners ought to generate different chemical properties and ought to generate different catalytic properties. And to some extent that's true. It's not always true, and we'll return to say something more about the catalytic consequences of this later. And the remaining figures here simply give you a few examples. In this case, face-centered cubic. The center 2 are for the hexagonal close-packed structure. The right-hand are for body-centered cubic. But the principle remains the same. Corner atoms have a low coordination number. Atoms sitting in a face have a higher coordination number. And the question that one faces is, does this or does this not have catalytic consequences? So I might just return to this previous sheet. What we've said just a minute ago deals with hypothetical metal particles of ideal crystallographic shapes. In fact, almost always, the particles which are, say, between 10 and 50 angstroms in size, present in highly dispersed metal catalysts, appear to have, so far as one can judge, appear to have shapes that are non-ideal. They're very often approximately spherical. The consequence of this departure from ideal particle structure means that the number of surface atoms which are of low coordination, which are abnormal, I should say perhaps abnormally low coordination, such as corner atoms, the proportion of surface atoms that are of abnormally low coordination is even greater in these non-ideal shapes than it is in the ideal shape. And if we pass over the next slide and have the next two diagrams, and you'll see, if you turn to diagram 10, how this increase in the number of corner atoms can arise. If you have a, if you start, for instance, if you carry out a thought process, if you start with a flat surface, and then start to bend it, how is, at an atomic level, how is this curvature accommodated? The curvature is accommodated by a step structure. That is to say, of course, atoms being indivisible, one can't cut through the center of atoms. The curvature is accommodated by moving through steps. And if there is a, and this is indicated in this diagram here, it's a step structure which results in a curvature in this direction. And if you have curvature in two directions, that is, if the surface is also curved this way, then that curvature around a second axis is accommodated by putting kinks in the steps. And here you are, kinks in the steps here. So this is the general sort of structure of non-ideal surfaces which have some degree of curvature in them. It's very common in practice. And if you look at this, of course, you see immediately that an atom which is sitting in a corner position, and more particularly an atom which is sitting in a kink position, is rather similar in its low coordination to a corner atom in an ideal crystal. And this then is the origin of the statement I made a few minutes ago, that practical catalysts which have quasi-spherical metallic particles in them have an abnormally large proportion of surface atoms in those particles that are of a very low degree of coordination, and which therefore might be expected, if one can choose the reaction correctly, which might be expected to have high reactivity. Let me now go back, and I'm sorry to jump around like this, go back and have a quick look at diagrams 8 and 9. Diagram 8 looks a bit of a mess. It's taken out of the structure of metallic catalysts, where there's an atlas of these things. All it does is to give you some idea of the fact that both the fraction of total atoms in a surface, the fraction of total atoms in a crystal which are present in the surface, and the fraction of atoms with given numbers of nearest neighbours is strongly dependent on the crystal size. Now these two diagrams refer to the top one, both of them refer to face-centered cubic structures. The top one is for an octahedrally shaped crystal. The lower diagram is for a cubo-octahedral crystal, and if you refer back to that previous diagram showing crystal shapes, you'll find both of those lists shown there under the face-centered cubic classification. And all I want to point out is the obvious, that is to say that as the particle size increases, d relative, and I'll explain what that is in a moment, but it's a parameter, it's a dimensionless parameter for crystal size. As the crystal size increases, of course, the fraction of the dotted line, the fraction of surface atoms present, the fraction of the total number of atoms present in the surface decreases and goes to 0 when the crystal size is infinitely large. And then also the fraction of surface atoms with various degrees of coordination also changes fairly rapidly over this relatively small size change. The curve I equals 9 refers to atoms sitting in a 1-1-1 face, and I equals 7 and I equals 4 are defined in the diagram for the octahedral crystal that's in one of the previous sheets. And the second diagram simply is the same sort of thing for the cubo-octahedral shape. D relative. D relative is a dimensionless parameter which is useful since it enables you to use these diagrams for any particular metal provided you choose the crystal habit correctly. And it's defined at the bottom of this sheet. It's defined down there. What it is the diameter of a spherical volume, which equals n times the single atom volume, n being the number of atoms in the particle in question, divided by the atomic diameter. The atomic diameter, of course, is simply the nearest neighbor distance in the crystal. That happens since you're defining the size in terms of n, and the single atom volume and the atomic diameter are in effect crystallographically determined parameters, and you can put numbers to them for any particular metal. And then diagram 9 gives you a feel for what is the situation for an actual metal, in this case platinum. Diagram 9 is the percent of surface atoms which are corner atoms, as distinct from atoms in a close-packed face, for octahedral and cubo-octahedral crystals, plotted against the actual particle size, which is taken as the maximum dimension of the particle from corner to corner. And all I want to point out to you is you see the percent corner atoms for very small particles approaches 100%. In fact, in the case of an octahedrally shaped crystal, every atom is a surface atom, and every atom is a corner atom when the crystal size is, I think it's 13 angstroms. But the change in percent of corner atoms is very rapid over the particle size region from about 10 angstroms out to about 30 or 40 angstroms. Right. Let me just sort that out. Before moving on to say something about electronic properties of small particles, I just want to point out one thing which is often overlooked. That is, the surface structure of metals is not not necessarily an unchanging property of the metal. It can depend upon reactions that occur on the surface. Page 11 says something about this. If one takes a single crystal surface, that is a flat surface, with the average surface being flat. If one takes a single crystal surface and treats it particularly in an oxidizing atmosphere, the surface may rearrange and break up into something which diagrammatically can be represented here as a mixture of a complex plane, that is a high index plane, and a low index plane. And the reason for this is that particularly oxidizing reactions, which is where changes in surface morphology of this sort are most often found, processes occurring in oxidizing atmospheres often generate considerable energy at the surface, like in the first instance the reaction between hydrogen and oxygen on the surface of copper. or the reaction between oxygen and ammonia on the surface of platinum. And the latter reaction is of course a commercial reaction for the manufacture of nitric acid. Considerable energy is generated locally on the surface, and this locally generated energy is enough to cause atomic mobility, and under oxidizing conditions the oxygen is usually absorbed to some extent on the surface of the metal, and the oxidized surfaces have their free energies changed by comparison with the free energies of the virgin metal surface in a manner that makes the faceted structure more stable thermodynamically than the initial flat structure from which it was formed. There's been, just in passing I might point out, there's been a great deal of work of this sort done with faceting of platinum in the oxidation of ammonia. As you might expect, it's an industrial process of considerable importance. And even if you start with a polycrystalline wire, which is traditionally the style of catalyst that's been used for that process, one always gets extensive surface rearrangement of this style, and the structure of the working catalyst is almost always not what you think it is, because it's broken up into a rough sort of structure of the sort shown at the top of the diagram. Right, let's move on and say something now about electronic properties. What we're really concerned with here is addressing the question, to what extent might the electronic properties of small metal particles be different from the electronic properties of the bulk metal? And it's useful to, at least to, even if one can only speak qualitatively about this, which is the case, at least in these lectures, it's useful to address the question because it implies that if there is a difference, then the chemical properties of small particles may also be different. I wanted, for the sake of convenience, I've divided this up under three headings: so-called intrinsic small particle effects, effects which result from the surface structure of the small particle as distinct from the particle as a whole, and thirdly, electronic effects which result from interaction between the particle and the support. And let's begin with intrinsic small particle effects. Reflect on the following. The work function of a metal is the analogue of the electron affinity of a single atom, or the ionization potential, I should say. Suppose I take a single atom of platinum and remove an electron. The work done is the ionization potential, the energy required for the ionization process. If I take a lump of platinum and remove an electron, the work done in removing the electron to infinity is called the work function. And generally speaking, with metals, the ionization potential of a single atom is considerably in excess of the work function. From memory, the work function of platinum is about it's about 5 electron volts. The ionization potential, the first ionization potential of a single atom of platinum is well in excess of 8 electron volts. And so if you ask the question, what happens to the energy required to remove an electron from a lump of platinum as I reduce the size of the lump, there comes a time when the energy required to remove an electron must change, even though it may be quite a small particle before the change becomes significant. And that is in fact the case. How is one to make an estimate of how small the particle has to be before the energy required to remove an electron differs appreciably from the work function of the bulk metal. That problem was addressed has been addressed in some detail over recent years, and I don't propose to do anything other than give you a sort of hand-waving answer, which is correct in order of magnitude, but doesn't really say too much about the detail. If in a metal, like in a molecule, in a metal, the electrons exist in energy levels, and as a rough approximation, you have one quantum state per electron, and you have as many electrons, order of magnitude, as many electrons as you have atoms in the crystal. In other words, if you ask what is the average spacing between the quantum levels of the electrons in a metallic crystal, what is the average spacing between the levels, it's of the order of the Fermi energy divided by the total number of atoms or electrons present. And that, of course, results in general in the average level spacing being very small, extremely small. And the fact that the average level spacing is very small means that metals are conductors at room temperature, because the electrons can be promoted thermally, or something equivalent to that. So the simplest way to approach the question of how small does a metallic particle have to become before it has electronic properties differing from those of the bulk metal is to simply say how many atoms can you have which will make the average level spacing roughly the same as the thermal energy at the temperature at which you're going to make the measurement. And if you say, well, I'm dealing with room temperature, the thermal energy is kT, which is about 2.5 by 10 to the minus 2 eV, and you get about 2.5 by 10 to the minus 2 eV when the number of atoms in the crystal is about 400. And that corresponds roughly to a crystal that's about 20 angstroms, 2 nanometers across. So as a hand-waving sort of guess, it's not unreasonable to say that small particles that are of the order of 20 angstroms in size and smaller will probably have electronic properties that are significantly different from those of the bulk metal. And in fact, it goes in the direction, as you might expect from the argument that I presented to you at the beginning of this little discussion, by comparing single atoms with crystals. It goes in the direction that as the particles get smaller, below 20 angstroms, the energy of electron removal increases. That is to say, if you want to use an electron for a chemical process at the surface of the particle, then you've got to pay a higher price in energy to get hold of the electron as the particle size goes below 20 angstroms or thereabouts. There has in recent years, in fact, been a fair amount of work of a more sophisticated type dealing with the density of states as a function of particle size. And for our purpose, it's just useful to note that the density of states for small particles converges towards the bulk value, the bulk density of states, when particles have sizes in excess of a few tens of atoms, which is, say, 1.2, 1.5 nanometers, which is, for our purpose, not, we can say it's in reasonable agreement with the result we obtained from this collective electron model, which I described to you a moment ago. Okay. effect does the surface have? We've already noted that in the surface, atoms have less than, of course, the full complement of nearest neighbours, and atoms which exist in the surface in corner positions have an abnormally low number of nearest neighbours. Now that was, that realisation was discussed quite a long time ago by Jeff Bond, who used the terminology of dangling bonds for surface atoms which lacked full complement of nearest neighbours. And the proposition was that if an atom had a number of dangling bonds, these could be used in adsorption processes. And there is some truth in this. It is possible to provide some rationalisation of adsorption phenomena from a dangling bond approach. But it's by far, it really doesn't come to grips with the quantum chemistry of bonding at metal surfaces, and that latter is a problem which, although it's being worked on still at the moment, is not really something that's been adequately solved, at least to the extent which it can be used predictively in the manner that valence theory can be used predictively in for bulk molecules, for ordinary molecules or the like. So I draw your attention to the dangling bond model. It may or may not be useful. Something related to it, that is calculations of the presence of extra orbitals with energies near the Fermi level, that is to say with energies which are useful for bonding at the surface. Calculations of this sort have been made over the years. Jennings, I believe, was the first to have done it, but a number of people, including the people at Berkeley, have spent a lot of time on this. And there are undoubtedly conclusions which are valid to the effect that atoms which sit in low coordination positions possess extra orbitals with the required which exist in the required energy range, extra orbitals in the required energy range suitable for bonding. But again, the problems of symmetry, or the lack of symmetry of the surface, has made a predictive theory difficult to obtain. And I'm sorry to be able to have to say that at the moment I don't believe there's anything of a predictive nature yet that can be usefully said beyond that. I turn finally to particle support effects. Generally speaking, small particles of the size 20-odd angstroms and less cannot exist by themselves. They have to be sitting on a support. And if they are sitting on a support, what effect does the presence of the support have on their electronic properties, if any? And the answer is, in general, it does have an effect. The support does have an effect, but the nature of the effect is fairly strongly dependent on the chemical identity of the support itself. What this sheet does is to just first of all at the top is to summarize some of the quite large body of data, and gives you some idea of the sorts of things that have been observed. There is really quite a lot of data now which shows that small platinum particles sitting on the surface of gamma alumina, or sitting on in the internal surface, on the internal surface of, say, Y zeolite, that small platinum particles, which are typically 10 to 20 angstroms in size, behave as though they're electron deficient. They behave as though the interaction between the platinum and the support has made the metal more electronegative, makes it more difficult to extract an electron. There are some similar data for platinum sitting on carbon, in which there's ESR data which shows that the carbon can act as an electron traps. And in that case, what one observed was the ESR signals from electrons in the support, but the electrons came from the platinum. So the platinum is, again, in principle, to some extent, electron deficient. And there have been a range of quantum mechanical calculations for various metals, but particularly silver, sitting on various supports. And again, much of this provided some indication that there was a general movement of electrons out of the particle into the support. So, roughly speaking, there is reasonable evidence that very often very small metal particles are electron deficient relative to the particle which exists in principle by itself. And the lower part of this sheet just gives you an idea of at least one bit of data which refers to platinum on a zeolite. I think it was Y zeolite. I haven't made a note of it. It's XPS data where one has looked at the electron binding energy of the platinum particles sitting in the zeolite. The line studied was the 4d 5/2 line, and the dotted line rising as you move to the right in the diagram is the binding energy, and the reference point is the binding energy for that line for the electron in bulk platinum, which is about 314 volts. The horizontal axis is a measure of particle size. Now I apologize for not having written that in terms of actual size, but I took the diagram actually out of the journal. What it is the measured ratio of hydrogen, adsorbed hydrogen atoms, experimentally determined, adsorbed hydrogen atoms to the total number of platinum atoms present in the material. In other words, on the basis that one chemisorbed hydrogen occupies one surface platinum atom, what that ratio is really a ratio of the number of surface platinum atoms to the total number of platinum atoms present in the dispersed platinum. And the indication down here is simply to give you a feel for where you are, that when that ratio is about 1 to 1, the platinum particle size is about 13 angstroms. So, in other words, you're dealing here with as you go in this direction. As you go in this direction, you're going in the direction of larger platinum. As the platinum particle size increases, the binding energy approaches the bulk platinum value, or to say it in another way, as the platinum particle size decreases, the binding energy for the electron in that level rises, and it rises by, over that range, by something of around ½ volt, so it's not a trivial matter. Does that have any chemical consequences? Well, it undoubtedly does. We'll return to that problem of chemical consequences in a moment, but let me just give you a couple of general statements. Electron deficient platinum was discussed, it must be 10 or 12 years ago now, in relation to the formation of adsorbed anionic species such as sulfur 2-. And in general it was found that when you worked with systems in which the platinum particles had an enhanced electron affinity, that is, the work of electron removal increased along the lines of that diagram we saw at the foot of the previous page. When you had very small platinum particles in a suitable support such that the energy of electron removal from the platinum increased. It was more difficult to form adsorbed sulfur, which resulted in a reduction in the extent of sulfur poisoning for hydrocarbon reactions. One thing. And the second thing, which we'll briefly return to later on, is the fact that when you have electron deficient, or when you have platinum which is from which it's more difficult to obtain electrons, there is an increased propensity for hydrocarbon skeletal isomerization, and we will have a little bit to say about that later on. But before leaving this, I want to turn to just say something about strong metal support interactions. With noble metals such as platinum supported on titania, the situation is rather different, and it's been the subject of a great deal of work in recent years, because it offers some possibility of obtaining dispersed platinum with special properties. I think it's fair to say that in fact in practice the expectations haven't really been realized, but let's just say something about what goes on. When you have platinum supported on titania, when the platinum is reduced in hydrogen at a sufficiently high temperature, the platinum becomes at least partially inactive towards hydrogen chemisorption. And that arises, it's now fairly clear, from the operation of two effects operating simultaneously. One is that in the high temperature reduction of platinum titania, the titania is able to migrate over the surface of the platinum to some extent, and there is an encapsulation effect. That is, the titania which migrates, and you can regard it, if you like, as adsorbed TiO2 on the surface of the platinum. The titania on the surface simply acts as a blocking agent and prevents hydrogen chemisorption. However, there is very likely an actual electron transfer effect taking place at the same time, and this is summarized in those two equations at the bottom of the sheet. That is to say, under reducing conditions, some of the Ti4 plus is reduced to Ti3 plus, and the Ti3 plus functions as an electron sink with relation to the platinum particle which is sitting on the surface. In effect, it can dump an electron back into the platinum particle. The platinum particle functions as an electron-rich particle, which tends to inhibit hydrogen chemisorption, and in fact has an effect also on the ability of a platinum particle in that situation to carry out other hydrocarbon reactions. I don't propose to say any more about it at this stage. Very briefly, we'll make a start now on saying something about alloys, but we won't be able to get past the first sheet or two, but it'll be useful to get going. Ultimately, I'm going to say something about the structure of dispersed alloy particles, that is, small alloy particles, but we need to begin by discussing something of the surface chemistry of alloys in general. The most important thing we need to address is, if you have an alloy of two components, I've called them here L and M, one usually cannot assume that the surface composition of the alloy, irrespective of whether this is a small particle or a large particle or massive metal, one cannot assume that the surface composition is the same as the bulk composition, and in general it will not be so. And it will not be so because the two components, L and M, taken separately, the two components are almost certainly going to have different surface energies. And so if you make an alloy of these two components, the free energy, the total free energy of the system, can be minimized if the component with the lower surface energy accumulates in the surface. That is to say, there will be a migration of the component with the lower surface energy from the bulk, which is depleted thereby, from the bulk to the surface, which is thereby enriched. How does one calculate the equilibrium situation? The equation at the top of this sheet is the relevant expression, which is in fact an exact statement. X means mole fraction. X means mole fraction. Delta HA is the enthalpy of absorption, and delta SA is the entropy change for absorption. And what we'll do on Wednesday is explore how to use that expression to say something, even in a semi-quantitative fashion, about what goes on in some specific cases. I think we'd better stop there. Thank you. Let me go back to the sheet we were speaking to at the end of Monday's lecture, which concerned surface segregation in alloy catalysts. I pointed out that the composition, the mole fraction composition in the surface of a alloy could be related to the mole fraction composition in the bulk. L and M simply refer to the two components of the alloy. B means bulk, surface means, S means surface. So that the ratio of mole fractions in the surface equals the ratio of the mole fractions in the bulk multiplied by this factor here, which contains both the enthalpy change and the entropy change. And of course, those of you who will recall elementary chemical thermodynamics will recognize that whole term there as being equal to the exponential of minus delta G over RT, the free energy, where delta G would be the Gibbs free energy. In principle, then, that equation will enable you to calculate what the expected equilibrium surface composition is, provided these terms delta H and delta S are known. And there's the problem. I thought it wise, for the purpose of these lectures, not to try and write out a detailed statement of how to calculate delta H and delta S, but I will refer you, if you're interested, I will refer you to what I think is the best treatment of that problem, which is by Williams and Boudard, published, as I recall, in Surface Science in around about 1976, quite a long time ago, which is based upon regular solution theory. You remember regular solution theory, which is established stuff for ordinary liquid mixtures, parameterizes the delta H of mixing in terms of nearest neighbor interactions, and evaluates the corresponding delta S term from ideal mixture theory. Well, the same can be done with a solid solution of an alloy. But the problem is that it makes both delta H and delta S composition-dependent terms. And since that is to say, that the delta H, for instance, involves knowing what the equilibrium composition of the surface is, and yet the equilibrium composition of the surface is what you're trying to calculate. So it's an implicit function, and it's a bit of a mess to evaluate, although it can be done. The remainder of this sheet, look up Williams and Badar if you really want to play around in some detail with that problem. The remainder of this sheet merely tells you, it's a restatement, that if one simply replaces delta H, the enthalpy change for the process, by the difference in surface energies of the two components L and M, and for the sake of argument sets the entropy change equal to 0. And it can't, the entropy change, in fact, for these sorts of problems is never very large, because you're really only concerned with differences in vibrational frequencies for the atoms in various compositions and in various positions, either in the bulk or surface. So delta S is usually not large. That's not a bad approximation. This, of course, is very gross, and it really isn't any good for doing quantitative estimations, but the rest of the slide merely points out, as you would expect, that, for instance, if the surface energy of L, component L, is less than the surface energy of component M, it makes delta H negative, and when you put a negative value for delta H up in this formula, you finish up with the obvious statement that the surface is enriched in component L, as you would expect intuitively from ordinary qualitative considerations. One of the problems you face in trying to do quantitative work with this sort of problem, that is the surface enrichment of alloys, which are solids after all, one of the problems is that the statement that appears at the top, that is this enrichment formula, while it's correct as far as it goes, it ignores a factor which is significant when you're dealing with a solid solution, but which is insignificant when dealing with liquids, ordinary liquid mixtures. And in liquid mixtures, the following is ignored as being trivial, if not absolutely zero. But in solids, it's never totally ignorable, and that is the effect of strain energy. You see, the problem is that if you have a solid solution, an alloy, in which the components, L and M in this case, have different molar volumes, that is, or to put it another way, in which the atomic sizes of L and M are different. If you replace L by M, you introduce a strain in the solid. There will either be, if it's too large, it will either try and push the lattice apart, or if it's too small, the lattice will close in upon it and strain the remainder of the lattice. And so that if you have the atomic sizes of the two components, or the same thing, their molar volumes, different, you will always have a strain energy. It turns out that's quite a difficult problem to treat theoretically, and it's really only easily treatable in the dilute solution approximation. And here's the answer. For G, the strain energy, written in terms of the molar volumes, remember this is equivalent to atomic size, of components, and I apologize here, I've gone back to using 2 and 1, whereas up here I was talking of L and M, but they mean that these are the two components in a bicomponent alloy, that the strain energy is proportional to the square of the difference in molar volumes, and since it's a square, it's obvious enough that the strain energy will be positive irrespective of whether component 2, say, has a greater or lesser molar volume than component 1. Strain energy is always positive. But that is in a dilute solution approximation. The net result of this, is, in a qualitative sense, is simply to, and this is the message you need to remember, that the effect of strain energy on an alloy is always to, in effect, to squeeze out, to try and squeeze out, to surface segregate, if you like, the minority component. In a dilute solution approximation, the effect will be to try and squeeze out the minority component, that is the solute, which will thereby enrich the surface. If you're faced with a situation where a dilute solution approximation isn't really adequate, then you've got almost an intractable problem on your hands and you really can't say anything about it. And if we pass on then, here's a little bit of data. Oh, I should point out there, if I might just go back to this one. I've written that as a proportionality. In fact, dilute solution strain theory gives you a term to stick in front of that, which will convert it into an equation, and that term which I've left out involves the elastic modulus of the various of the components that go into the alloy, and I left it out simply for the sake of simplicity. But in fact, that can be converted into an equation, and you can get numerical estimates for the strain energy in a dilute solution. And the table on the next sheet gives you some numerical values which I thought might interest you, since they're not particularly for the strain energy, they're not usually easily available in chemical literature, and this is taken from some work by Kelly from England, published in 1979, again quite a long time ago. The message really is that in many cases, but not all, in many cases, numerically the strain energy is small compared to the difference in surface energies. So this, in most cases, this is the dominant term. But there is one case here you see where the strain energy is really quite large. That's the gold-nickel system. And in that case, it would be reasonable to say, if you were trying to make an estimate of what would happen, that you certainly couldn't ignore strain energy, and in fact it might be in many cases be the dominant term. But except in the odd cases such as that, it's the surface energy terms which are important. And they will lead to enrichment of the surface by the component with the lower surface energy in the manner we've already described to you. And the next little table just gives you some actual comparisons of what's observed with what's predicted in a few typical examples. I've got three systems: the silver-gold system, the nickel-gold system, and the gold-platinum system, but I've grouped them into pairs depending on which is the majority and which is the minority component. In other words, when I speak here of solvent and solute, the solute is taken to be the minority component in the mixture. All right? And the middle column in the table tells you what the theory we've just been speaking about predicts. The tick tells you whether the measured observation, the measured concentration of the surface of the alloy agrees with the prediction, and the comment over here tells you why it's so. For instance, in the case of silver-gold, where silver is the solvent, that is the majority component, and gold is the minority component, the surface energy of gold is greater than that of silver, so you expect no enrichment of the surface with the solute. No enrichment. And that's what you observe. On the other hand, if you have the gold as the majority component, silver as the minority component. The surface energy terms predict that the solute, that is the silver, should segregate to the surface and enrich the surface, and that is in fact what's observed. In this particular case, the atomic sizes of gold and silver are almost the same, so that the strain energy should be trivial. In fact, it is apparently so. The gold-nickel system, the middle case, refers to the one I drew your attention to in a previous table. That is where the strain energy is very large. And what happens here is that in the case where the solute gold, which has the lower surface energy, where the gold is the solute, the minority component, the behavior of that system is dominated by the surface energy terms. It predicts that the solute will enrich the surface because it has a lower surface energy, and that's what's observed. But in the case where the gold is present as the majority component, nickel is the solute, the nickel has a higher surface energy than gold, and yet the solute also, that's the nickel, enriches the surface, and that's because of the very large strain energy in the system, which, when the nickel is the minority component in a dilute solution, it's squeezed out. And gold and platinum behave in much the same way as this one up here, because G is small, because there's not too much difference in atomic size between platinum and gold. So, just to summarise the situation, you can make qualitative predictions moderately with some reasonable reliability, provided you take some account of both surface energy terms and strain energy terms. But remember that except in a few circumstances, of which nickel gold is one typical example, strain energy is often not too big. So far, in all of this discussion, I've been confining attention to, although I haven't explicitly said it, I've been confining